In this section we will talk about how to measure surface tension, using a simple experiment with a thin circular wire. Then we will make some observations about what affects surface tension, talk about the units and value of tension force, and work through an example. Then we will discuss force on a soap bubble, the force on a droplet or bubble, and then finally we will work through another example. The force due to surface tension, using a simple apparatus, like the one shown here. That consists of a thin circular metal wire that is connected to an accurate vertical balance. The wire is dipped into a liquid such as water. Then the force that is measured by the balance is observed as the wire is pulled out of the water. We will make a plot of the force divided by the weight of the wire versus the depth to which a wire is submerged. The weight of the wire is equal to the density of the wire times the gravitational acceleration times the volume of the wire. When the wire is fully submerged within the water, the forces acting on the wire are gravity and buoyancy. The force measured by the vertical scale is equal to the weight of the wire minus the buoyancy force that is exerted by the water. Substituting rho wire GV for W and rho water GV for the buoyancy force, we get that the force is equal to rho wire GV minus rho water GV. Assuming that the density of water is equal to half the wire density, then we get that the force is equal to rho wire GV minus 1/2 rho wire GV, which is just 1/2 rho wire GV. But notice that this is equal to 1/2 of W. In other words, the force measured by the scale, divided by the weight of the wire, is equal to 0.5. Assuming that the height of the wire within the water is equal to 0 at the surface, the scale gives this reading of 0.5 for any wire height below 0. When the wire is at the surface of the water, a peak force is observed. In this case, the force that is measured by the balance is equal to the addition of the weight of the wire and the surface tension force of the water that is acting on a wire. We assume in this case that the observed surface tension force is equal to 0.1 times the weight of the wire. Hence, the force is equal to W plus 0.1 W, or 1.1 W. Hence, the force measured by the scale, divided by the weight of the wire, is observed to be equal to 1.1. Finally, when the wire is pulled clear of the water, the force that is measured by the balance is exactly equal to the weight of the wire. In other words, the force measured by the scale, divided by the weight of the wire, is equal to 1. Let's review. We've observed that for this particular wire and liquid, the ratio of the force that is measured by the balance to the weight of the wire when the wire is submerged is equal to 0.5, and the force ratio when the wire is at the surface is 1.1, and the force ratio when the wire is above the surface is 1. Press the play button to replay the movie. Then when you wish to continue with the lecture, please press the play button at the top. Now that we know conceptually what will happen when a thin wire is pulled out of water, let's try to evaluate the value of the surface tension force, based on some observations from this experiment. First, we note that if the wire length is doubled, by doubling its radius, the surface tension force is also doubled. This implies that the surface tension force varies directly with the length of the wire. Our second observation is that if the thickness of the thin wire is doubled, the surface tension force does not change in any appreciable way. This implies that a wire thickness has no effect on the surface tension force. Finally, we observe that if the circular wire is replaced with a plate that has the same radius, the surface tension force is reduced to half its value. This means that the surface tension force on a wire divided by the surface tension force on a plate of the same radius is equal to 2. This implies that the surface tension force acts on the periphery of objects that are in contact with water. The peripheral length of the plate is equal to 2 pi times the radius of the plate. The peripheral length of the wire is twice the peripheral length of the plate, due to the fact that the wire has both an external and an internal peripheral length that is in contact with the water's surface, as the wire is being pulled out. The value of the surface tension force can be obtained based on the aforementioned observations. The surface tension force varies directly with the length of the object's periphery that is in contact with the water. Hence the surface tension force is equal to a surface tension coefficient, which is denoted by the Greek symbol gamma, times the length of the object's periphery, or L. In the case of a wire, the length of the internal and external parapheres of a wire of negligible thickness is equal to 2 times the circumference of a wire. Thus the surface tension force that acts on a circular wire as it is being pulled out of a liquid is equal to 4 times the surface tension coefficient, gamma, times pi, times the radius of a wire. The surface tension coefficient has units of newtons per meter, or dynes per centimeter. The conversion factor between the two units is given as 1 newton per meter is equal to 1000 dynes per centimeter. In other words, 1 millinewton per meter is equal to 1 dyne per centimeter. The shown table gives the surface tension coefficients of several common liquids when they are in contact with air at room temperature, or 20 degrees Celsius. The surface tension is given in millinewtons per meter. Note that the surface tension of water is 72.8 millinewtons per meter. We will use this information in the following example.